Very nice to be back here in Amsterdam. Last time I was here, that was around my defense, and so I'm happy to be here to attend to defense two of my amazing past fellow PhD students. And okay, so for the old time's sake, I'm giving a talk now, and this is a work in progress, which is almost done. It just always takes. I mean, there are lots of subtleties that I am hiding from you in this talk, but we expect this to be out in a few weeks. And so I had the fortune to work with this interesting topic with some amazing authors. Hamiltonian H, who was visiting this Monday, even Szegedy-type, a PhD student from Temme was not contact, and Michael Castellano from Copenhagen. And well, this talk is about a topic which is quite physicsy. So I tell you that it could be that there are some heavy jargon, and please don't hesitate to interrupt me and ask questions. You know, I'm coming from a computer science background, so I try to use as much computer science language as I can, but maybe I think infected too much by physicists by now, so I don't know what it is. Okay, so I wanted to start with, I tried to build this up slowly because I think it includes concepts that may be not so familiar to some of you. And so I want to start from the classical side because everything has a very nice analogy, but it takes a few steps to get there where I want to really talk about. So I start with the classical Metropolis-Hastings algorithm. In this algorithm, the goal is to sample from some unknown distribution. Sorry, the distribution is known, but maybe it's not known what's the normalization, and then we don't know how to sample from it generally, but still we know the distribution, but we don't know how to sample from. That's the starting point. And so one example that physicists look at, and this is a classical model, but classical statistical physical model, is that you have some Ising system which consists of n spins, which has like 0 ones or like plus minus ones. Think about that way, and you have some interaction term between pairs of these spins. There's also some energy term associated to sides. So that would be this. This is the kind of energy for sides, and this would be the interaction term between sides I and j. So this formula, this Hamiltonian, if you wish, tells us what is the objective function of or the energy of some configuration. And in statistical physics, when you look at thermal states, then they have this so-called Gibbs distribution, where the probability of finding some site in your system in a state is proportionally minus exponential of the energy of the system, and this beta is the inverse temperature, so it's 1 over the temperature. And so we know like the relative weight between every two configurations, but in order to know the exact distribution, we would normalize this. And for that, we would need to know the summation over these exponentially many configurations. Because we have n bits, we have 2 to the n possible configurations, all the n bit strings. And so it's a very difficult problem to compute this in a normalization factor. And how people try to solve it sometimes is that they have some Markov chain, which they call exploratory Markov chain. So this is just something that does evolve on the configuration space. And in this Ising example, people often just say that let's pick a random site, a random spin, and flip it from minus to plus or minus or plus to minus. And so this is just a walk which kind of, it's like walk on the hypercube, so it relatively mixes quickly and so on. And we hope that we can modify this in some way, that now it will sample from the target distribution we wish. If you would just do the walk according to this flipping, the uniform distribution would be the stationary one. But we want this Gibbs distribution to be the stationary distribution because we want to sample from it. And so let's see what is the Metropolis-Hastings rule, how to change this exploratory Markov chain to a new Markov chain which will sample from our target distribution. And the rule is very simple. You pick a configuration, sigma, and transition to a new one according to your original walk. So just pick one of the widths and then see what you get. And if the probability, the relative probability of this term is larger than where you were before, then you accept this move. So it means that if the energy went down, that means that the associated weight is higher, then you accept this move. However, if the direct probability after the move is smaller than where you were before, so it means that the energy is actually increasing, then you reject this step with some probability, which is somehow proportional to how much is the how much unlikelier is this new configuration than the previous one. So it is 1 minus the new probability versus the old probability. Because you divide these things by each other, the overall normalization factor just falls out.
So these sigmas, what are the values of them?
Yeah, so yeah, maybe it was not the best notation. This is a configuration. So it's a bit string of length n consisting of plus minus ones. And so that's a spin configuration. And so it's like move from one configuration, one bit string to a new one.
And the P, the Markov chain?
The Markov chain is take a random site out of the, random bit out of the n1 and flip the value. That is the original Markov chain. And now the modifying the Metropolis hastening is do this, but with some probability, if your energy is increasing, then you actually don't do that step. So as opposed to just blindly following the original Markov chain, you think about, okay, did this move actually decrease my energy? If it did decrease, I'm happy because it kind of intuitive nature kind of wants to minimize energy, so it's kind of going in the right direction. But if I am going a bit up, then well, then I accept it with a smaller probability. I don't always accept it.
Is this reversible?
Yeah. So yeah, indeed, this modified Markov chain has nice properties. One thing is that stationary distribution is proportional to this Gibbs state, and actually the way you prove that this is a stationary distribution is that now this new walk is reversible with respect to the stationary distribution, which is proportional to tau. And this is, yeah, so this, one can show that this new random walk, this new Markov chain will have this detailed balance condition that if you are in this distribution proportional to tau, then along each moves, you kind of exchange the same load. That's the detailed balance condition. Yes?
Yeah, so yeah, as a question regarding the sigma, I mean, I'm still a little bit confused about what is sigma I sigma j in your Hamiltonian. So it's like the polymatrix or
yeah, it's following matrix quotation. So in this slide, yeah, sigma is just a configuration of plus minus ones. Minus one, plus one to the n. And then sigma I is just the value of the ith bit, the ith spin.
And the same as capital N, your slide is capital N.
Capital N is 2. No, capital N is 2 to the lowercase.
Number of fixed reactions.
Yeah, so because you have n bit strings, your overall configuration space consists of 2 n configurations.
That's like rise P fix for real values from n for big N times big N.
So I didn't hear the question.
Markov chain, you say that P is a matrix with real entries from big N times big N.
Yes.
So that describe, I mean, you would apply, because you cannot apply P to that sigma. Like what is it, a transition matrix?
So sigma is a particular state, and you have a distribution over the states. That's a vector of length 2 to the n, to the like low uppercase n.
It acts on computation.
Yeah. So this acts on distributions. You have a probability distribution, and you apply a Markov step. You have a new distribution.
Okay, so you apply P to the distribution over this.
Yes, and so
that describes the Markov.
yes, but these transition rules are sort of the the columns of this matrix.
On line C1 asked if P is symmetric.
Well, it doesn't have to be.
It is normally.
Yeah. It's most of the case it's not.
But it's symmetrical, right? It's symmetrizable by scaling with tau.
Yeah. So it's reversible, the Markov version, sorry, the Metropolis version, and so then you can make it symmetric. Okay. Well, and actually there are some nice properties of this Metropolis modification. In some sense, this is the closest Markov chain to P, which has this reversible property with respect to this target distribution. And another nice thing is that often this dynamics converges rapidly in physically motivated examples. Yes.
So just before we continue, I think I forgot the definition of reversible. Does that mean that, what does that mean in this context?
Well, it means that if you are in this stationary distribution, then basically the probability that you transition from your site to the next one, or so like take any two sides, then the exchange probability between any link is the same in both directions. And that obviously proves that it's stationary because if the exchange is everywhere the same amount, it doesn't change. Okay, so now this was the better known version of Metropolis things. Now I'm moving to the lesser known, the continuous time variant, which is really the same thing in spirit, just now you work with continuous time Markov chains rather than discrete ones. And so those can be described by some generator L, which contains the infinitesimal jumps. So these off-diagonal elements of L are the non-negative jump rates, like at unit time, how likely is you to jump along that direction. And the diagonal entry is just minus the sum of the off-diagonal elements, because I mean, if you are jumping to several sites with some probability, then your presence at your current site decreases with the sum of those. So it's an infinitesimal jump. And well, actually, you can think about these jump operators as a Laplacian of a weighted directed graph. It's like the same thing, just in different language. And so how you get a Markov chain, which describes how your state, like your distribution evolves after time t, just exponentiate this generator time t. So e to the TL, that will be always a stochastic matrix and corresponds to t, like waiting for time t and doing this dynamics. Okay, and then you just modify this according to the previous thing, but now just infinitesimally. So once again, you look at your original jump rates and the new jump rates, which are the Metropolis version of your continuous time quantum walk, is that if the jump is in the direction where the probability is increasing, you are moving in the right direction, then you accept it. So that means that this tau is the tau modified Metropolis algorithm. And then if the probability increases or the energy decreases in physics language, then the jump rate is the same. So you accept every such infinitesimal jump. However, if your probability is decreasing after a move, your target probability or the energy increasing, then you accept it only with this proportion. So the rejection step is again with infinitesimal. Every jump is rejected with the same, like how much your energy goes up, it's proportional to how likely is you to reject it. And so this is really the same rule, just now you do everything infinitesimally as opposed to discrete way. And now you have the new generator, and this new generator is that you just can run in times, sort of saying. Once again, this modified generator has nice properties analogous to the previous ones. So the station distribution will be proportional to this target distribution. And we don't need to know the normalization for implementing it. And well, so this, I mean, maybe reversible doesn't make sense in terms of the generator, but the generated Markov process will be reversible with respect to this distribution. And once again, from math perspective, it's nice because in some sense, this generator is the closest to the original one, which has these stationary properties. And because it's very similar to the discrete contribution, it still often converges rapidly in physically motivated situations. Okay, so now this was a classical Metropolis sampling, discrete and continuous version. And now quantum Metropolis sampling. So then the change is that now we have objective function, which is a quantum Hamiltonian, which is non-commuting. That's the typical case. So just sticking to the example that we had before, now the Hamiltonian, this objective, like energy function changes. For example, we replace this on-site terms by in the x basis. So these are still ±1 spins, but now we are adding an energy term on site in the x basis, plus-minus basis. And this makes these terms no longer commute. And so this is a Hamiltonian which consists of non-commuting terms. It has no longer this very nice integer like spectrum as before. Everything changed a lot. It is potentially much more difficult, but you can still define what is your target. Your target is to sample from the Gibbs distribution, which is now a matrix which is not diagonal in the computational basis, but still it's a density operator if you normalize it properly by its trace. So once again, as before, we knew how likely is two configuration compared to each other. And to get a probability distribution, we need to normalize the entire weight. And here again, to get the actual quantum state, we will need to divide by the trace of this matrix. And that gives us the Gibbs state. Once again, we want to sample from it, but we don't know the normalization factor. It's very hard to compute in general. And so the recipe is very similar. We have some sort of exploratory quantum process or channel, which can be the same as before. It can be just, again, pick a random spin and flip it. So apply this X gate on the J entry for a random cyclic J. So a J qubit for randomly cyclic J. And okay, so the quantum Metropolis algorithm was a paper by Temme et al. 2009, but accepted in Nature 2011. And they basically just do the same thing, but now analyze this random process in the eigenbasis of the Hamiltonian. So they actually think about this as a walk on the eigen states of this Hamiltonian. And so if you are at some state psi and move to lower energy psi prime state after such a step of this exploratory quantum process, then you accept the move. On the other hand, if you are increasing your energy, then you reject with some probability which is proportional to like how much your energy went up.
If this is a walk on the eigenstates, then you should also start with some eigenstate, right? How do you get that?
Well, you don't have to. You can just start in. Okay, so usually you just start in a uniformly random state, but that's the identity density operator. So in any basis, if you pick a uniformly random bit string, that corresponds to a maximally mixed state. The maximally mixed state is maximally mixed in any eigenbasis. So by picking a random bit string, you actually pick a random eigenstate. Okay, so if you define it this way, actually the stationary distribution will be the Gibbs distribution as you want it, because everything just reduces to the same analysis as the classical one. Basically, the same thing happens. It's just that your exploratory quantum walk looks like something more difficult, but really everything can be analyzed in the eigenbasis.
Tau is now a density matrix, right? A normal, a not necessarily normalized density matrix.
Yes.
So applying x sub j means something like applying x sub j to the right and x sub j star to the left of that tau.
Yes.
And what's the meaning of evaluating the energy?
That's the issue. That's the red thing in the line. So you need to compute the energy because you need to decide whether you accept the move or you reject it. So how do you evaluate energy? well, we have phase estimation that evaluates energy. So that is something that we could try. Problem is that phase estimation is not a, well, because you have a non-commuting Hamiltonian spectrum can be dense. So you have probably super tiny gaps. And then but you can't accurately know the phases, only roughly with phase estimation. And that introduces some trouble. And that trouble is that I wanted to talk a bit more about, and then this is actually the issues that we overcome. So there are two issues. You need to resolve the energy. Let's say if you do phase estimation, you resolve it approximately, and so your accept reject probabilities are roughly okay. Intuitively, it should be fine. But then there is this other problem that you have this reject step. So you do this complicated process. You have your eigenstate. Suppose you measure your energy using phase estimation. You make a move using your exploratory quantum channel. Then you measure the energy, and energy says, well, kind of went up the energy, so probably reject. You flip a coin, you reject, and you go back to the previous eigenstate. Sounds trivial, right? Well, it's not. And then they use the very complicated Marriott-Vatrus kind of thing. And if your energy estimation, your phase estimation would be perfect, then somehow you make everything like projective in some sense, like telling you definite answers. And then this Marriott-Vatrus trick is letting you move back and forth between two measurement results, sort of, intuitively speaking. If you know this result, then hopefully you can follow. If not, believe me that this is what it does. But somehow, in its original form, it only works if somehow your projectors are perfect. It can exactly distinguish somehow energies and so on. And then this Marriott-Vatrus thing also, although it's kind of complicated, it works. But now the problem is that none of your energy measurements are actually accurate. They are not like saying a yes, no answer. Am I below a threshold or above? No, well, you are most likely above the threshold. These phase estimation measurements give you information like that. And so this Marriott-Vatrus analysis just breaks down. And so in this original paper, Temme et al. Tried to somehow overcome this issue, and they used a boosted version of phase estimation, which makes sense. You want only a few outcomes with high probability. That can be done. And for analyzing this process, they needed an additional property, which is shift invariance. And they said, well, both of them can be done. That's right. So we just do them together, and then we solve our problem. Except that shift invariant boosted phase estimation is provably impossible. Like, I tried really hard to implement this, but the original method didn't really work. And I threw all my toolbox at it. Nothing worked until I talked to an undergrad student with whom we figured out actually there is no such thing. That doesn't exist. It's for some topological reasons. Okay, so what is shift invariant phase estimation? If normal phase estimation, you start with a register, which is 0. You apply Hadamard's, and then you have uniform superposition over some key values over, I guess, square root m. And then you apply your phases. So you have this eigenstate. You apply your phases, which will be something like e to the it pi over m. Yes, divided by. Okay, so this is just somehow you apply a higher power of your unitary, and that puts. Sorry, I'm messing it. Speed up something. I should have some phi, some phase. This is the eigenphase. And then yes. And then you apply quantum Fourier transform, and you hope that you get something like phi out. This is only hope, because if your phase is somehow not a multiple of like 2 pi over n, sorry, like 1 over n, then it doesn't work. But you still get some distribution which is peaked around the correct value. Now imagine that you initially don't do a Hadamard, but do quantum Fourier transform. I guess here I should have an inverse maybe. So just do a QFT, well, nothing changes. Hadamard or QFT does the same thing for superposition.
So what is the vibe that you work together?
Well, that is some binary description of the phase.
I see it's
And I guess sorry, the eigenstate is surviving.
like a bit strange.
Yeah, but I mean there is some annoying superposition here. So just like high level. Okay. Now if you start with not zero here, then you can still do this circuit. And this will just somehow add something here. So if you start with K, then you already have some phases appearing here, which just go through. And what you will get is something like P plus K. Okay, so you started here with some initial value, and this initial value just shifts your ultimate outcome. This is shift invariant phase estimation, which is ordinary phase estimation is shift invariant if you just do a QFT at the beginning, not a Hadamard. Okay, and now you wanted to do this, but also that these amplitudes are highly concentrated around the true value, like after boosting. And these two things together just cannot be implemented always. So like there is always some problem about yes.
What do you mean by boosting? Is it like sort of increasing the number of bits of picking, or is it repeating a few times and taking?
Well, boosting is basically killing out amplitudes, killing out phase estimation results that are far from the truth, which you can do with this median tree.
So you
But-
do this multiple times in parallel, you take the median of your different outcomes in superposition.
Yeah, that would be the standard way of boosting, but here that wouldn't work because you want superposition over labels, not multiple labels. And so this is where the analysis just goes wrong. And actually, there is no way of fixing it. It's like impossible to implement such unitary in general. There's some continuity issue. As you continuously change the pace, something always goes wrong in a nutshell. Anyway, so they were hoping to solve this issue using this shift invariant boosted phase estimation, which is a good idea, but unfortunately doesn't work. And then there is another version of this Metropolis algorithm, and they just assumed that phase estimation is perfect, so they basically just didn't touch this issue, which is unphysical assumption. And then there is this newer one by Watson and Temme from 21, and they use a continuous time quantum Metropolis algorithm, which I will talk a bit more about. And their solution to the problem is that they assume that the spectrum has periodic gaps. So periodically it just has parts of the spectrum which is vacant. And then you can make your phase estimation outcomes again somewhat deterministic. But this is unfortunately once again unphysical assumption. And only very recently, building on their work, they were able to prove a Metropolis version which actually doesn't require these unphysical assumptions.
András, why do you say it's unphysical to assume these periodic gaps? Do you mean like not all systems will have this, or like, 'cause I could imagine system could.
Yeah. So people typically want to do this Gibbs sampling for this transverse phase Ising models, Heisenberg models, and so on. And these condensed matter systems usually have a very dense spectrum. Like coming from random matrix theory, it has this semicircular law and something like that. The main important thing is that the gaps will be exponentially small. There will be no large gaps, so maybe some, topologically relevant. There is one gap or two gap, but not like exponentially many large gaps or something. Why not exponentially? So yeah. So this really is a stringent requirement on your gaps should be somewhat periodically appearing and large. This is really, not unusual. Okay, and now we attempted to solve this problem, and we are building on this continuous time quantum Metropolis framework of Watson and Temme. And so our solution to the problem is to apply that phase estimation and operator Fourier transform. So I probably see the proof. Can end it here. So yeah, like what is depth phase estimation and what is operator Fourier transform. These are things that I didn't know before I started on this project. So I would like to explain these to you. But before like explain these techniques, let me revisit now the continuous time quantum metropolis algorithm, which I didn't talk about yet, but it's completely analogous to the classical one, but needs some new notation. And by the way, physicists call it a dynamical semigroup. And it's well, dynamical because it has to do something with time, and semigroup because if you evolve first for time t1 and then for time t2, it's the same thing as evolving in one go from time t plus 1 t2. It's like the same property that has continuous time quantum Markov chain. Due to the Markov property, whether you like do a t1 time step and then t2, that's the same as doing it in one go, basically. So that's why it's semigroup, and that's why dynamical, because it has to do with time evolution. And that's why it's also not a group, because you cannot invert it. This is like a dissipative process. So of course, some Markov process cannot be inverted. That's why it's only a semigroup. Anyway, so now this is just terminology. And now, like this is how you write this infinitesimal generator in the quantum setting. So this is the Lindbladian, it's L, and this dot represents that you should put there your density operator. Your current distribution is a quantum state, but now a mixed state. And so whenever you have this quantum state, these are the so-called jump operators. And this tells you kind of the infinitesimal jumps that happen to your state. You sandwich your quantum state with kj dagger. And think about this as like the diagonal terms of this Lindbladian. So this is kind of telling you that how much the state moved away from the current position. This is just to make everything like preserve, trace, and so on. Really think about this as just the minus term in the diagonal of the Laplacian. These jump operators, which makes you change the state.
Notation on the left side of the equal sign suggests that this is not the Lindbladian, but the dagger. Why is that thing there?
Because physicists, okay, quantum mechanics, there are these two views. You can act on states, or you can act on operators. And in the traditional physics literature, Lindbladian acts on the operators, and the Lindbladian dagger acts on the states. It's just tradition. Yes. And once again, similarly to the classical continuous time Markov chain, you get the time t evolution of this quantum state, this quantum channel corresponding to time t evolution, by exponentiating this Lindbladian, which is now a super operator. You exponentiate the super operator and get a new super operator, which will be this completely positive space preserving sort valid quantum channel. Yes.
Yeah, so I'm wondering, you mentioned that it's a semi-group because if you apply this operator for some time t1 and t2, then it's the same as applying for t1 plus t2. But I presume then that the fact that this is not a group means that t1 and t2 are restricted to be, let's say, positive.
Oh yes.
Yeah. Okay. So you see, and maybe you'll come to this, but I'm wondering. It's not obvious to me why you now enter into some sort of dissipative context, if you will, because you're not describing a dissipative system, right? So
yeah, okay, so this is a very good question. Actually, Lindbladians are what basically some version of a master equation, right? And so this is a purely dissipative system that I described. In general, you could have some Hamiltonian term which kind of accounts for unitary dynamics, but I don't want to have it here just for simplicity.
right, but this is just a tool to describe a non-dissipative system.
No, this is a dissipative system. Right. Like a Markov chain is also doing kind of some stochastic dissipation. And okay, so where it comes from actually, or is describing quantum thermodynamical systems. So thermalization. You have some system interacts with some bar. There is some process going on. It makes it converge to the thermal Gibbs state. Sure. So I mean, we want to give sample just limiting what nature does, or like what we believe nature does approximately. Right. So really, this is a physically motivated way of something Gibbs states.
But just to be clear, the physical, the condensed matter system that you're describing are non-dissipative in general, right? Or are you?
So
You also like that?
yeah, the system itself is non-dissipative.
Yeah, you
And then
mimic
there is a
this.
bigger bath and there is some interaction which, yeah, so like
Oh, okay, yeah.
it's a system bath interaction and then yeah, like there's this infinitely large or like extremely large bath and the interaction with that kind of entangles your local system with this very large system and that kind of entanglement is lost forever. And we look at the subsystem, it looks like dissipation.
Yeah.
Sure. So I guess you can also say that the Gibbs distribution, the stationary distribution of the Lindblad kind of process, where you couple small system of interest with the infinite bath.
Yeah, right.
Now we just devolve, and what you should obtain for a state of a small system is the Gibbs distribution.
Right, yeah.
So this is one way you can formalize.
So in this sense, it's a tool. Yeah.
Yeah. So really think about this as some like more complicated version of this Laplace operators that we exponentiate. And so, like looking at this intuition, I think it's hopefully instructive what this Metropolis modification should be of these infinitesimal jump operators. So as I told you, this first thing, this KJ terms, these are the jumps, and then the other thing is just making sure that everything is trace preserving, just and also the diagonal of this Laplace operator. And so we should just focus on how to modify the jump operators, and the rest just accordingly modify a formula. I don't want to go into details. The main conceptual thing is how to modify the jumps. So, well, the jumps in particular can take an eigenstate psi and jump to a new eigenstate psi prime. And in this case, with what probability should I accept that infinitesimal jump? Well, with this ratio of the energies. So if energy decreases, I accept it. If it doesn't decrease, then I accept it only probability, which is proportional to how much the energy went up. So, yes.
What things are you summing over here? What are psi and psi prime?
Oh yeah, sorry. Yeah. So J, that are all the original jump operators, and then psi and psi prime are just the eigenbases twice.
Eigenbases.
Sorry, eigenstates of the Hamiltonian.
The Hamiltonian that you omitted from this picture.
Well, the Hamiltonian, which is the describes the energy of the system. So I want to sample from a Gibbs state, which is given by the Hamiltonian, and I have an exploratory process, which is this Lindbladian. And I modify this exploratory process such that the unique stationary distribution will be the Gibbs state. And this is how you do it according to the Metropolis rule. And I hope that this analogy now kind of makes sense to this. And by the way, this thing is called by the physicist Davis generator. And so, yeah, I mean, this Metropolis-like, maybe they don't exactly have this modification, but something analogous, which has the same effect ultimately. And somehow these jump operators, they sort of come from how the system and the bath interact, and then like what is the system, like bath Hamiltonian and these details. The derivation is kind of complicated, but somehow in physics, this just comes from the coupling and the effective description of this coupling to large bath. Okay, so this is something that physicists would call a Davis generator, and this is how they describe and understand how a system thermalizes. We can view it from a computer science perspective as a Metropolis modification of some exploratory Markov chain or quantum channel. So this is what we want. But once again, to have these acceptance rates exactly, we should know the energy difference, which is the difficult part. We can't do it because of these issues with phase estimation. There is actually this principle called the time energy uncertainty principle, which says that if you are looking at your system only for time t, then you can only resolve its energies up to precision 1/t. Basically, this is this principle in rough terms, and that's exactly the same thing in phase estimation. You need to go up to powers of this unitary t to get the phase resolved to resolution roughly 1/t. There is a physics name of this as well. Okay, well, there is just some short intermezzo. Suppose that you have these jump operators. Now, one question is, how can I simulate this Lindbladian? Okay, mathematically speaking, it's exponentiating a super operator, but this looks very complicated and unclear how efficiently you can do it on a quantum computer. And actually, for this work, we devised a new Lindbladian simulation scheme, which is very simple. And so what it requires is that you have a block encoding of your jump operators. So you have a big unitary matrix. At the top left corner is something that encodes the J, the jump operator, labeled by quantum state J. So this is your unitary that somehow encodes the jumps. And while using these jump operators, you can do a weak measurement. So there is your quantum system rho and some ancillas. You apply this block encoding, which kind of applies these individual jump operators. But then you only, so what this rotation here does, okay, maybe it's kind of complicated looking, but it's just a rotation. So says that if you see something other than zero, so if some of the jump happens, that means if some of the jump happens, then look at this register with a tiny probability. So it's a weak measurement. It's not that you look at this label completely, but only with some probability delta. So it is like a square root delta angle rotation, which corresponds to looking at this label with probability delta. And if you don't look at, so that means that you don't look at, it means a zero in this square, then you reverse the dynamics. So it kind of says that only apply this measurement with a tiny probability. And well, so how it does it, applies this block encoding. Then if there is some measurement happening, which means that some J appears there, then kind of save it a little bit. The rest of the state actually inverted. And that will be actually roughly a delta time step of this evolution. Okay, and so this is actually analogous to first order trotterization, as opposed to simulating some of Hamiltonians. You simulate a little bit one of Hamiltonian and the other one, and the same error scaling is here. So how you should choose your data is such that somehow the evolution, epsilon precise evolution for time t will be something t squared over epsilon, number of weak measurement steps ultimately. And this can be improved. There is a more elaborate scheme, which is by Cleve and Wang, and they achieve an essentially optimal simulation complexity, which is something like t times log 1 over epsilon. So t is the simulation time, and that's essentially optimal, but that is more complicated, kind of hard to explain how it works, but this is just really do weak measurement and apply it typically. Okay, so there is a slightly less efficient but easy way of implementing invariance, and there is a more efficient one. You can use either one of those. Okay, but now we have a block encoding of these initial jump operators that's perfectly reasonable, but we wanted to have the modified walk. Sorry, can I get some water? Is there over there on the other side? You're right. Okay. Yeah, he's just calling. Dissipating one. Become a jump operator. He's now in a different state. It's reversible. Yeah. Okay, so we have way to simulate it. Hopefully it's convincing enough. But okay, how to do it in our case? for this, I would need to talk about damped phase estimation. All right, so what is this? So this a little bit of insight about how discrete Fourier transform relates to continuous one. And this is, again, something I didn't know before this project, and I think it's very interesting. So you have your usual continuous Fourier transform. You have some function, and you apply this well-known integral formula, and it Fourier transforms your function. In particular, if you have a Gaussian, then it will invert the variance. So if your continuous function is just a Gaussian with variance sigma, it will be a new Gaussian with variance 1 over sigma. But can be like any function, like any sufficiently nice function can be Fourier transformed continuously. And we have this discrete Fourier transform, which is over n capital N elements. And what's the relation between the two? It was kind of mysterious to me. But it's a very nice thing that actually, if you take a continuous function and you wrap around a unit circle, a complex unit circle, then these two operations kind of commute. If the function is sufficiently nice, then doing a Fourier transform there and wrapping around the Fourier transform is the same thing as first wrapping around discrete sampling along the cycle and then discrete Fourier transform. And so for this to work, yes? You periodically sum up. You periodically sum up. And the periodicity is the circumference of this cycle, which is, to make this work, it's square root 2 pi n. So somehow, for this identity to hold, this is the periodicity you should use.
How do you come around? How do you go then from some discrete thing to a continuous?
Well, okay, maybe this green light should be going only down. So maybe going this like horizontally and down is the same as going down and down. Yeah.
So that this is some kind of, say, quote unquote conformal mapping that you how to say, you map the far ends of the continuous function to the opposite side of the circle with respect to where you have the peak. Like I'm imagining two functions you drew on the top. You are putting them on a circle, and so they are decaying. They are concentrating in some finite interval, and so this finite interval gets good enough representation on a circle, and the low part, the parts that are, let's say, can be ignored. They are pushed on the other side where there is a small amount of samples.
Exactly. So if your variance is, somewhat reasonably smaller than square root 2 pi n, then this wrapping around essentially just you can forget about the tail after the periodic summing. And then very accurately we will get the Gaussian wrap like again, just now concentrated more. And only very small mistake you make in this picture. Exponentially small actually, yeah, in terms of like the ratio between the sigma and pi n. Square root pi n. Okay, so why I'm saying this? Because now this is a new way of doing phase estimation. That you don't start with this uniform superposition or like some adding some phase to it, but you start with a Gaussian distribution over your peaks. Now you apply your phase and do Fourier transform. What you will get out is approximately the Gaussian, which is now, well, so basically what you will want to do is sigma will be something not too much smaller than square root 2 pi n. And so 1 over sigma will be something not too much larger than 1 over square root 2 pi n. So the ratio between the variances is like n. So indeed, basically your precision will be basically 1 over n. Like in Fourier transform, like phase estimation, you do this n up to n power of unitary, And you can resolve energies up to precision 1/n. Now, this happens the same way here, but now you have some Gaussian waveform, so Gaussian amplitudes around it. Okay, so now this is a way of doing boosting in a much nicer, physically motivated way. Okay, yeah, so, okay, what I didn't say you here is that if you just apply this, this phase, which is depending on the tick where you are, that is just, that's multiplication by a phase, and in Fourier transform, that's a shift. So if here you multiply with a phase, that will be a shift under continuous Fourier transform. So this phase will appear just as a shift. So where this peak will be, it will be just peaked around the phase value that you want to estimate. And then this comes from the fact that pointwise multiplication after Fourier transform is a shift. And you do pointwise multiplication by applying higher powers to your phase. And after Fourier transform, you get your shift, which tells you highly concentrated your estimate around the true value.
Sorry, like in your the picture, I guess maybe you want things to be the other way around, that for the initial state, you want the variance to be large. And then once you Fourier transform it, then it should be.
Yeah, exactly. So initial variance will be that this peak is almost covering the entire circle, but still has like somewhat small tail.
You're kind of starting from the right corner. And then
Oh yeah, actually, yes.
you're basically saying instead of uniform superposition, just have a Gaussian that is very.
Yes.
Like a uniform, like this.
I don't.
I didn't really follow, like somehow the uniform superposition of like a just super wide.
Yes. Okay. Good question. So yes, but then so infinite limit is that your uniform superposition over an infinite line, sort of, and then you should get infinite precision. But now the problem is that yes, you can wrap around this infinite superposition, but the problem is that if your phase is not appropriate, then the wraparound part would like to get different phase than other wraparound parts. So, okay, so when you wrap around uniform superposition over the cycle, then it has different layers. Different layers correspond to different points, which should get different phases. And they get the same phase at every layer, if and only if it's a multiple of 1/n. So exactly when phase estimation works exactly, that's when wrapping around is compatible with pointwise multiplication.
Okay, so you want like a Gaussian that's like as wide as possible, but this still being able to wrap nicely around.
Yes, exactly. Otherwise, you don't know like what phase to apply to that amplitude. Indeed, so that's why it will be like somewhat spreading around the cycle, but still has a already kind of decayed tail by the time it wraps around. And this, by the way, gives you the same complexity. If you do the math, if you want your epsilon precision with delta probability, then somehow the complexity is this log 1 over delta over epsilon. The same thing that you would get with this median of means tree. The standard boosting gives the same complexity as this one, but this is just doing it in one go.
Can you say again why this is an advantage for you? Like what is better here compared to the median?
Yeah, very good. That's the next slide. So remember that we had these jump operators. We already had the block encoding of them, we could assume. But now we want to have the jump operators of the modified, the Metropolis version. So if I just look at a single jump operator K, if I could somehow decompose this jump operator by the energies, so nu is a label of energy differences, and K nu is the transition between subspaces where you increase your energy by nu. Okay, so K nu is you look at the matrix elements. Oh, sorry, there is a typo there. This right side should not have the prime. So on the right, very right, that should be psi psi. So you jump from psi to psi prime. That means you increase your energy by nu, and maybe they are multiple different pair of eigenstates that have the same energy difference, then you just kind of collect them together. And so your jump operator can be decomposed according to like how much jump happens in that subspace. Yes.
I'm a little bit confused about the ket multiplying the matrix. I'm not sure what's going on there. Is it supposed to be a bra or is it some funky tensor product that I'm not understanding?
Well, okay, if you wish, initially there could be a 0, doesn't hurt anyone, and k. And now you want to decompose it to something like sum over.
He's asking, what does this mean?
Yeah, what does that mean?
I think you have a tensor for this.
Oh, yeah, I guess. Oh, okay, yeah. So, and in particular, if I would omit this, so sum over nu, k nu, is just k itself. I just decompose like it just jump according like how big jump it does and just collect the terms. Okay. And if I could, now this is just an identity, just trivial decomposition, but now I wanted to actually label that, okay, this part of the jump is actually making this big energy change. And if I have this label there, then I can accept it with the probability that I need to accept it with. So if I could somehow label parts of the jump with how much jump it does, I would be done. So this is what I wanted to do. But now this is like Fourier transform. I have some superposition or like linear combination of things, and I just want to label them with the energies. And now there is a version of Fourier transform, which is the operator Fourier transform, and you can just do it on operators. So you start with your, say, this Gaussian function I told you, some initial weight function. So this is just the role of the initial weights in phase estimation, and now this is the operator you have. But now what you have is you apply Hamiltonian simulation with minus the time, then apply the operator k, then do this simulation again, but now with positive time. And so if you are in the part of this operator where you have a energy difference nu, then this plus evolution time and minus evolution time, that just comes out to something like, yeah, okay, so look at this, e to the I h k nu, e to the minus I h t. Well, then I know that it is somehow energy psi prime and has difference nu. So that is actually the same thing as e to the I h nu times k nu. Okay, so somehow this complicated matrix, because I'm at the right subspaces, it just becomes a scalar. So I have this scalar, sorry, and there's a t here, which I forgot. So this is exactly like applying the phase in phase estimation. And then I do a Fourier transform, and what I will get this k nu parts of the matrix, and then labeled with the appropriate value of nu, while with the Gaussian noise around it. So this f hat, this would be the Fourier transform of f. And in this case, and in case my original f, my original weights was a kind of wide Gaussian, it will be a narrow Gaussian centered around the true value of this jump. And so now what I got is basically approximately just nu labeling k. So I know how big jump I did. And well, actually, it's already a block encoding of it. So I just do operator for transform. Then additionally to the original jump labels, I also get a label which tells me how big energy the jump represents, up to very high precision.
What is it by label? I would understand what you say if ket W or ket U. Is that typo or do I?
Okay, so think about, so this is the Fourier transform of the function, and think about this as approximative Dirac delta. So it is 1 if the argument is 0, so it will be 1 at nu.
Oh, I see. So the only part that has support is where W equals nu.
Well, yeah, and with a small Gaussian around it. And so as you see, it is not exactly what we wanted. It will not get us the exact labels, but something close to it. And already gives it us in the form we needed for invariant simulation, so we can just do invariant simulation. Well, and then the other, I don't know, 20 page or 30 page of our paper is that actually the small issue is that you don't have the exact right jump rates, exact modification, but somewhat right. We introduce a notion of an approximate detailed balance. So your Gibbs state is approximately preserved by these jumps because they are approximately doing the right thing. And then it approximately means that you have an approximate eigenvector, which is approximately Gibbs state you wanted. And that's why we are still working on like writing out this 70-page paper. It's Gaussian, yeah. With, yeah. And well, I have some open questions. Well, in which physical systems can we expect rapid convergence? Because then we could just use this algorithm and simulate that system in a quantum computer nicely. And one thing I didn't mention so far, but somehow the speed of convergence to the stationary state is dependent on the gap of this generator. And while this will be some cases nice, some cases not, but what techniques we can have in this complicated non-commuting setting. How noisy is the algorithm? Interesting question here, because usually quantum algorithms, when you add noise, they just break down completely. Like this one bit of thing that goes wrong in Shor's algorithm, probably answer is completely garbage. However, this algorithm simulates nature. What nature does, there is some noise and it kind of pumps it out. It's dissipative. So if some noise happens in the algorithm, well, it's just like thermal noise, it gets pumped out. So one or two noise happening maybe doesn't hurt the algorithm that much. It's a hope for a somewhat noisy algorithm. Final question is garbage computing. Maybe we are one for carbon capture. Thank you.